Thank you, Brian, and welcome everyone. Glad you are back for this fourth and final session in our series. And you should see two documents on the screen in front of you. If you don't have those up, I'll encourage you to get those and get them ready. But in case you were wondering where they're coming from, I'm going to pull up the website, our website for you real quick, just to give you a sense of where to find that in our codes and standards section under publications, and then under 2015 wood frame construction manual you can get a free view only version of the wood frame construction manual. And then you can get a free download of the workbook that we are working from today. So wanted to make sure you knew where to get those, and if you haven't already and want to download them, you can do that while Brian comes back and leads us into our first poll, which will give us a sense of who's in our audience today. Brian?
Okay. Quick note with the polls, please don't put an answer in the questions or chat box. You can select your answer directly in the poll window. And I'm going to launch the first poll here. And that is, what is your profession? We have A, architect, B, engineer, C, code official, D, building designer, or E, other. I'll give everybody a few minutes, not a few minutes, a few moments here to put in their answers. Just a few more seconds. All right, I'm going to close the poll and share the answers. We have 3% architects, 73% engineers, 18% code officials, 1% building designer, and 5% other. So pretty good spread there, and we thank all of you for joining us today.
Okay. Thanks, and welcome back to those of you who have been with us. In your workbook, then, for Part 4, we're going to be on page 51 of the workbook. Page 51, first story design. We'll concentrate pretty heavily today on wall framing and wall sheathing, and then probably skip over floor framing and floor sheathing, jump into connections. We'll skip over anything that we've covered in the past so that we don't duplicate a lot of information, and so we'll be going through a lot of new stuff today, but it may seem like we're skipping past a lot of information. So if you haven't joined us before, they're all recorded and available for you on the website. So the next page, 52, is wall stud design. We've looked at both load-bearing and non-load-bearing stud design from the wood frame construction manual, so we are going to skip past that today. Last week we also talked about top plate design and how those top plates act as diaphragm cords and how we design those, and so we're going to skip past that as well today. We also did header design last week for that second floor, but last week we were able to make built up multiply 2x material work. I'll just point out to you on page 54 of the workbook that the solutions and the tables also include solutions for glued laminated timber, glue-lam. And so one of the first solutions for a 9-foot header that we have in one of the walls, it's a big, either big oversized sliding glass door or French doors, something like that, required a 3 1/8 by 13 3/4 inch glue-lam. I can't remember if we tried to get a 4-ply to work, but that would probably mess up our wall system because we've got 2x6 walls, and a 4-ply would probably exceed what we're doing there with 2x6s. So the glue-lam works and fits, and even has a little bit of room left over for some insulation for energy requirements. Another thing I'll just point out at the bottom of page 54 is that if all of your first floor headers align vertically with the second floor headers, only one floor is being carried, and you could probably design those headers for a little more efficiency. So just be aware of that, but also note that your jack studs would still need to be designed for roof, ceiling, and 2 floors, because the jack studs are still carrying those vertical loads around the headers. So that's a note there at the bottom that hopefully would be helpful to you if you're sharpening the pencil and trying to create some more efficiencies in the design. Also note, however, that not all the windows from the second floor line up with what's below, so you have to be very sure that everything's lining up if you're going to do that. We also talked last week about the exterior non-load-bearing wall headers and the tables for those, interior load-bearing wall headers and tables for those. Again, we used glue-lam here just to give some variation to the design examples for header design. And we mentioned non-load-bearing headers can be up to 8 foot long 2x4s flat for interior non-load-bearing headers in accordance with the IRC. So that shows up at the bottom of page 55. So we're keep on going here to page 56 and start into some shear wall design. Again, before we do shear wall design, we probably look at the suction loads on our panels, and we see that if we do that in accordance with tables 313A and B, that the minimum panel thickness just to resist the suction loads for 160 mile per hour exposure B is 1530 seconds. So that's really our starting point for a panel thickness before we even do our shear wall design. So I want to point out this first elevation here, 1-2, which is the north elevation. When we look at our shear walls here in a second, we're only going to have time to look at one shear wall to give you a kind of a representative idea of what we're doing with shear wall design. It's a 40-foot wall with that 9-foot opening that we just talked about for header design. Note that the length of full height sheathing is 25 feet, so those are the full height panels. There's a 3-foot panel here at the right on either side of the window, and a 16-foot long panel between the window and door, and another 3-foot panel at the end. And we'll talk about aspect ratios here on the next page, but just get a kind of lock that away into your memory as we scroll on into the next page here, page 57. Talked a little bit about aspect ratios. So for wind design, the aspect ratios for wind design is 3.5 to 1. And so that's going to be, since we have 9-foot walls in this particular structure, that's going to be about 2.6 feet. We've got 3 feet is about the smallest full height segment that we have, so that meets those aspect ratios. For seismic design, however, the code says the minimum aspect ratio is 2 to 1, but there is an exception that talks about allowing a 3.5 to 1 aspect ratio as long as we take some adjustments, and we're going to talk about those adjustments again like we did last week. Also want to point out the aspect ratios for gypsum, and that's a limit of 1.5 to 1 for unblocked gypsum and 2 to 1 for blocked gypsum. And so we'll talk about those nuances here a little bit as well. This is our standard detail for walls in the wood frame construction manual, and it basically shows here 6-inch perimeter nail spacing and 12 inches in the field for the wood structural panels, and then 7 inches around the perimeter and 10 inches in the field for the gypsum. And so we're assuming wood structural panels on the outside at 6 and 12, and gypsum, half-inch gypsum on the inside at 7 and 12 as our baseline shear wall. Okay, we'll show some variations of that today based on one of the tables, but that again is our baseline that you want to be aware of. So now on to page 58, and we're going to first look at a segmented shear wall design. So the segmented shear wall, if you recall from last week, means that we're going to have hold downs around each individual shear wall segment that we design. So typically between the window and door openings. The full height sheathing is what ends up being our segments. So you end up with hold downs around window and door openings. The perforated shear wall method that we'll talk about on the next page allows us to move those hold downs to the corners, but we'll need to fully sheathe the walls. So again, we're going to just look at this one wall, 1-2, and I want to start with the effective length here of full height sheathing for seismic, and it's got 22 feet with an asterisk. So the asterisk down here at the bottom of the table, down here, says that per table 317D footnote 4, again we talked about that last week, that if you take a 2B over H reduction for exceeding that 2-to-1 aspect ratio for seismic, that you can go as high as 3.5 to 1. So these calculations here in walls 1-1 and 1-2 are just what we do to take that 2B over H reduction for an effective full height sheathing length. So that's where that 22 feet comes from, where we show 25 feet of full height sheathing. Because of that 2B over H reduction, we're at 22 feet. So then last week we talked about going into the table 317C1 to come up with that 18 feet of required sheathing. Again, we're not going to repeat a lot of that information, just want to kind of refresh your memory. And with that, even for this first floor wall, the 6 and 12 nail spacing works, and we've got enough sheathing. Even with all the adjustment factors, it requires 20 feet of full height or of sheathing length, and we've got 22 feet, so we're good for seismic. Going into table 317A like we did last week, it would require 19 feet that we'd pull out of the table, and with some of the adjustment factors it turns out to require just about 22 feet of sheathing, but we don't have to take that reduction like we do for seismic, so we're going to compare that against 25 feet of full height sheathing. So that works for wind, and so we don't have any problems here with the segmented approach. Note, however, for walls 1-1 and 1-B, we did have to go to 4 inches on center for the exterior nail spacing, but I'll show you in a second how we came up with that. So let's jump then to the perforated shear wall method, and that's on page 59. And what we're seeing here is a lot of red, or if you've got a printed out copy, it's a dark shade there that shows that several of these walls now don't work for the perforated method. And again, as you have to recall from last week, that for this perforated shear wall length increase factor from table 317E, we go in with a percent of full height sheathing based on what's required by the segmented method and our maximum window and door openings, and it gives us an effective or an increase factor, a perforated length increase factor. In this case it's 1.43, and that would require 28 feet of sheathing for seismic. Well, we've got only 22 feet of effective length, so that won't work. For wind design, it would require 30 feet for the perforated shear wall method, and we've only got 25. So we're seeing a lot of red here on the screen because the perforated method just doesn't give us enough full height sheathing to meet the demand for this first floor. The loads are much higher. So what do? Well, that's where we're going to pick up something new today on page 60, and so that's why I'm skipping over some things to get here, because this is going to be new information that we didn't cover last week. And so I'm going to jump to the wood frame construction manual, table 317D. So if you're following along with me, jump into your wood frame construction manual, table 317D. If you want to scroll there, And this is where we're going to pick up some new information today about how we can design for some variations in our shear walls. So keep that open, and I'm going to come back to the workbook here, and we're going to see what we have to do now to get this. First we'll start with the seismic wall. So this is for seismic design, and walls 1-1 and 1-2 didn't work for the perforated method. So again, in order to make this, to design with this perforated method, we have to go back and check and figure out how much shear wall we need for the segmented method. So we would then go back to table 317C1 like we did before, and when we look at table 317C1, we see that it requires 18.1 feet of sheathing for seismic, and there's a footnote there for the vertical distribution factor we talked about last week. It's 0.92, and so we're going to have to apply that one. So then here's the new one. In order to make this perforated shear wall work, we're going to have to reduce the nail spacing to 3 inches on center, down from 6 inches on center. And so to do that, we're going to use table 317D, and we're going to come up with a factor 0.53 that's going to reduce our length required down to something that's going to work in this wall. Okay, so over here in table 317D, page 222. I want to first show you your baseline, the baseline that we work with, and that's down here near the bottom of the table. So anything in a gray bar is going to indicate our exterior sheathing. So in our case, our exterior sheathing is 15/32 wood structural panels, and our edge maximum stud spacing, or our spacing, is 16 inches on center. And we've got 8-penny common nails at 6 inches on center. That's, again, our baseline. Then what's under that is what would be on the interior. And again, our baseline case is 1/2-inch gypsum unblocked. And we've got these cooler nails at 7-inch edge spacing. So if you look, for you engineers in the audience, there are our capacities: 436 pounds per linear foot for wind, 239 for seismic, and that's because we don't count the gypsum for seismic design. Then we've got our aspect ratio limits, 3.5 to 1 and 2 to 1 for wind and seismic. And then our adjustment factors are 1 because this is our baseline. Okay? So we talked about that baseline case, 6 and 12 with gypsum on the inside. That's why these adjustment factors are 1. So I mentioned we're going to have to go to 3 inches on center to get the seismic walls to work. So to do that, I'm going to jump in the wood frame construction manual now to page 224. And we got to make sure we're comparing apples to apples here. So you go to 224 and you come down to the third gray bar there, and that's got the 15/32 wood structural panels at 16 inches on center. And we've got 8-penny common nails at 3 inches on center around the perimeter of the wood structural panels. And we've still got our gypsum on the interior, 1/2-inch gypsum wallboard. Even though we're not going to use that for seismic, we might end up using it for wind, so we'll just come over here and look and see what that gives us. It ends up increasing our capacity for seismic to 450 pounds per linear foot, just the same as if we had no gypsum on the interior. So this increased capacity is all due to the nails. The reduced nail spacing around the perimeter gives us that increased capacity, and you see for seismic that adjustment factor is 0.53. So the reason it's less than 1 is because back over here in our workbook, remember we're using tabulated effective or tabulated length requirements over here in the workbook of 18 feet, which is what's required for 6 and 12, but that 0.53 factor adjusts that down to just about half of what would be required. With all the other footnote adjustments, you see that it ends up being 10.6 for the segmented method. So it's 10.6 for the segmented method for seismic. So from there, then we jump right back into table 317E, which we looked at last week, based on the percent of full height sheathing in the wall. That's going to bump up our perforated shear wall requirement back up by about 50%, but it doesn't double it, just takes it up 50%, and that gets us to about 16.5 feet. As we talked about earlier, we've got 22 feet, so we're good. So we got that seismic wall to work by reducing the nail spacing down to 3 inches on center. And we worked hard to get that perforated shear wall method to work so we could move all those hold downs out to the edges. So that gives you a sense of table 317D, probably one of the most important tables in the wood frame construction manual for sheathing design. And I'm going to jump over there just for a second again to kind of reiterate a couple of things. So back to the wood frame construction manual, I'm going to take you to page 225, okay, page 225, and I just want to point out these footnotes down here, footnote 2 in particular, that we've alluded to earlier, but I just want to make sure you're picking up where this is coming from, and that's that the walls having an aspect ratio exceeding 1.5 to 1 shall be blocked. And this is all about the gypsum on the interior. This is footnote 2, which is always here on the 1/2 inch gypsum wallboard, and this is where the blocked versus unblocked gypsum is coming from. So I just want to make sure you see that. So it's 1.5 to 1, but as the minimum, but it can, if it's blocked, I'm sorry, let me just read it. The walls having an aspect ratio exceeding 1.5 to 1, this is for gypsum, shall be blocked, shear walls, and the maximum is 2 to 1. So you cannot exceed 2 to 1, and you can go as high as 1.5. It shall not exceed 1.5 to 1, and you can go as high as 2 to 1 if it's blocked. So that's coming from the AWC wind and seismic standard. So just wanted to point that out to you as well. The footnote 4 deals with the seismic provisions. That's dealing with allowing us to go to 3.5 to 1. And taking that adjustment factor of 2B over H. So research that. We've done that. The footnotes are important, and that's showing you why we're using those here in the workbook. So I'm back on page 60 of the workbook. We'll cruise on ahead to the wind design tables. Again, because 3 of those walls, 1-2, 1-1, 1-A, didn't work, we had to reduce the spacing down to 4 inches on center and 3 inches on center for one of those walls around the perimeter just to get that perforated shear wall method to work. But that was our goal, was to get the perforated shear wall method to work so we could get the hold downs to the corners. And so all of this exercise here is to accomplish that. You see the summary table here, table 6.8, that summarizes the segmented and the perforated. So you can see we can make the segmented method work at 6 inches on center, but that means then that we've got hold downs around each one of those segments. We reduced that spacing to 3 and 4 inches on center for a couple of these walls to move those hold downs to the corner. You'll see that in the details that we show at the end, but that's why we go through this exercise to get that to work. Okay, so that's it for shear wall design, And I think Brian now is coming back with a poll question to see how we're following along with that.
Sure am. Thanks, buddy. And let me bring up the poll. Oops. There it goes. Shear wall capacities can be increased by which of the following? A, reducing edge nail spacing. B, using thicker wood structural panels. C, using larger diameter nails. Or D, any of the above. So please take a little bit of time here to put in your choice. I'm going to give it a couple more seconds. All right. And here are the results. 22% of you said A, reducing edge nail spacing. 6% said using thicker wood structural panels. 1% said using larger diameter nails. And 71% said any of the above. So which is the right answer there, buddy?
Okay, and I guess I have to apologize. I probably wasn't as clear as I needed to be with this. Those of you that answered D are correct, but I didn't do a good job here in Table 317D of mentioning how you can get some of those increases other than talking about the edge nail spacing. So in Table 317D that I'm showing here on the left, this table, which is about 4 pages long, gives lots of options not only for changing the nail spacing, but also going with larger nails. Like you see here, a 10-penny common nail is going to increase your capacity, and going to a thicker wood structural panel, you see going from 7/16 here to 15/32 here, can also increase your capacity. So those of you that answered A, we're going by kind of what I taught there. Those of you who answered D probably have some experience there with shear wall. So I apologize, but those are all captured here in Table 317D as ways that you can increase your shear wall capacity. So back to the workbook, and I'm going to skip page 62 for floor framing and floor sheathing because that's very, very straightforward. We're going to jump to page 63, and the one thing I'm going to point out here, and we looked last week at table 3.1, but I just want to point out here the wall assembly to floor assembly connection requirements. Okay, and specifically bottom plate to floor joist or band joist, in joist. This is a requirement to handle shear that's going to be developed in those shear walls when we're connecting the shear wall to the floor diaphragm. And so table 3.1 has a footnote, and again, always look at the footnotes. They're always important. That says if the wood structural panel edge nail spacing is less than 6 inches on center, then you're going to have to beef up your nail spacing where you're connecting that bottom plate to the floor diaphragm. And so the default is 2 16-penny nails, but because we've got 3 and 4 inch nail spacing in the perimeter of our shear walls, we've increased the capacity of the shear walls, which means we've increased the shear between the bottom of that shear wall and the floor diaphragm. And so you see the number of 16-penny nails per foot is increased by about double. So take a look at those details as well, because that's not just pulling necessarily a value out of a table. You're going to have to do some additional calculations there to make sure you've got enough shear capacity. All right, then we jump to page 64, lateral shear and uplift connections. Again, if you haven't been with us before, up here in the top right of each of the pages kind of gives you a sense of what we're looking at as far as the design. And here we're looking at lateral shear and uplift connections for the wall assembly to the foundation. So we're going to be connecting, in this particular case, the wall assembly to a crawl space or basement. We'll show you some options if you happen to have slab on grade, but for the tables we're going to be in, we're going to assume connection to a crawl space or a basement. And so first thing we want to do is look at our seismic requirements here at the top of the table. and we're going to go to table 3.3A4. So if you're following along in your book, in your wood frame construction manual, let's go up here closer to the front and scroll down till we get to 3.3A4. And the reason we're in A4 is because we are assuming 5/8 inch anchor bolts. So up here in the top right, you can see some text here that gives you a good sense of what we're looking at. That's the anchor bolt diameter there, 5/8, and the ground snow load of 30 pounds per square foot. And so we're coming down here to size design category D1, which is what we're looking at. We need to know the length to width ratio of our building, which was 40/32, so we end up interpolating between 1 and 1.5. And we've got a roof ceiling and 2 floors. And then we're going to come across here for the minimum building dimension, which was 32 feet. So we end up interpolating between 3 and 5. Exactly in the middle of that is 4 anchor bolts required. So back over here on our table, that's what we pulled out based on a roof ceiling and 2 floors. So that requires 4 anchor bolts, but we always have to, again, look at the footnotes, and those footnotes are over here in the wood frame construction manual on page 169. Page 169, and I'm going to expand this so you can see a little bit better this footnote 5, because this footnote deals with that partial attic that we had. So when I said roof ceiling and 2 floors, I wasn't counting that attic space. I was just counting the 2 floors that are in the building, including the one on the basement or crawl space. But that partial attic is going to be picked here in this footnote 5, and we end up down here in the table with a factor of 1.14 to account for that partial attic space. And for just for clarity, what we're showing here is that we're picking up that additional roof and ceiling and some partition loads up there to account for that partial attic space. So we could, as we mentioned last week, we could have designed this conservatively as a roof ceiling and 3 floors, but this kind of gives us a little bit more realistic design, and so you factor that in. That ends up requiring 5 anchor bolts, and then you do ends up being 114 inches on center. I think the code's going to require something like, maximum of 6 inches on center for anchor bolt spacing. So you probably end up with 6 foot on center there for maximum spacing. But wind is going to end up controlling anyway, and that's going to take us to table 3.2A. So let's jump up here in the wood frame construction manual to 3.2A. Make sure you're in the right exposure category. Always look to make sure. So we're on page 155, exposure B, and we're going to look at the shear loads first. Make sure that we've got enough shear capacity. We'll have to jump to the bottom of the table for 5/8 inch anchor bolts, roof and 2 floors here is what we're looking at, and that building dimension perpendicular to the sill. We come across here to 160, and we end up with 9 anchor bolts to resist the shear. So we do the math and end up with 57 inches on center for that. So that's our shear check. Now let's check our uplift for those anchor bolts, and that's from table 3.2C of the wood frame construction manual. Again, make sure you're in the right exposure category, exposure B. We've got 2x6 sill plates. That's new, by the way, and so I'm going to show you something you need to change in your workbook here in a second. But for those end zones, and these are where the loads are higher at the end zones versus the interior zones just below there, we see that that spacing is 32 inches on center. So come back over here to the workbook. You see that we had 31 inches on center. Well, that was the previous version, so that's a mistake we're fixing. The previous version only tabulated 2x4 sill plates. We tabulated 2x6s to give just a little bit more, a few more options for you. And you see it gives you a little bit of relief on your anchor bolt spacing of 32 inches on center. And that controls over the shear design. So you may be asking yourself, well, you said at one point that we need to look at loads in 3 different directions: uplift, lateral, and shear. So let's jump to page 65, and that is for table 3.3. So I'm going to just jump to table 3.3 for. I'm sorry. Let's take a look at the wind loads. Sorry, table 3.2. Table 3.2 for wind loads. And the difference between the tables we were just looking at and these wind load tables is that this just shows you the loads, not the number of anchor bolts or number of nails or whatever we might be looking at. So on page 151, exposure B, you see that we tabulate, or we show uplift, lateral, and shear here in the header of this 160 mile per hour wind load, but for this crawl space or basement requirement, we don't show any lateral loads. We show an asterisk. And what does the asterisk say? Well, the asterisk says that anchorage required to resist lateral loads has to be determined in the foundation design. And this has everything to do with soil loads. So if you are designing that diaphragm, that wood diaphragm, to also pick up soil loads, then we got to make sure that that's accounted for in this design. So that's really why you see these kind of notes here, is because there are additional loads outside the scope of the wood frame construction manual. In this case, soil loads that we can't account for here in this particular design. So that's why you see those notes, and where you have to look to others, to engineering, to pick up that in the design process. Otherwise, those loads are shown there, and for lateral or for the shear and uplift design. So that's for the anchor bolts and connecting the wood structural panels, or I'm sorry, for connecting the diaphragm to the foundation. But there's one more part of the load path here that we got to make sure we account for, and that's the uplift straps. And that is getting the the shear walls, or the wall system, and the studs connected to that sill plate. And we could have done that one first. We didn't, but this is still something that we need to check. Now, if you decided to, let's go back up to one of the pictures here on page, top of page 64. Look at this middle diagram here at the top of the page. If you took your straps from the walls all the way down into the foundation system here, like we show at this middle diagram, rather than wrapping it underneath the bottom of the sill plate. So if you took the strap down into the foundation system, then you're done. You really don't have to do this next step. But if you wrap that strap underneath the bottom plate, then we're going to have to come over here on page 66 and look at making sure that we've got that. Now let me think about that for a second. Now we still got to size the straps, no matter what. I'm sorry, I misspoke. So if you take that strap down into the foundation, you don't have to design your anchor bolts for that uplift load. So you could skip that last step. You can't skip this step because we still got to get these walls down into the foundation system. So that comes from table A 3.4. We looked at that last week, and that's just showing the number of nails that would be required at one end of that strap into the wall system. And then if you wrap that strap down around under the sill plate or bury it down into the foundation, you don't have to worry about the other end. So that's what's shown there, and again, is the one step you need to make sure you account for, but you could get rid of some anchor bolts if you bury those straps in the concrete. So next page is 67, and that has to do with some overturning resistance, and I'm going to ask Brian to come back, if he will, and handle this next poll question.
Okay. And this one is: wind load connections between a wall assembly and foundation must be designed to resist A, uplift loads, B, lateral loads, C, shear loads, or D, all of the above. The answers are rolling in. And I'm going to close the poll now. And here are the results. 7% of you say A, 1% say B and C each, and 92% of you say D, all of the above. So, buddy, which is the right answer?
Okay, so this table is still shown here. Table 3.2 of the wood frame construction manual is a good indication of the type of connections that we need to design for: uplift, lateral, and shear. So we're always designing, looking at 3 different directions for our shear or for our connection design. So very good. Answer D is correct. All right, back in the workbook then for some uplift connections. If we decide that we want to get rid of the straps, as we talked about last week, there is a table, table 3.4b, and again, we covered this last week, so I'm not going to repeat it, but I just want to call your attention to one of the nuances here this week, because we start with our shear wall design, and for the segmented approach, we had 6 and 12 nail spacing for these walls, and so we can actually make this work for the segmented approach, where we can take the uplift through the wood structural panels and at 4 inches on center, and so we can handle both uplift and shear with the segmented approach. But for the perforated approach, you'll recall we had to go to 4 inches on center for one of those walls, 3 inches on center for wall 1-1. And so you'll find that when you get into table 3.4b, if you're already at 3 and 12, you just can't go any tighter. You in this case cannot use wood structural panels to also resist the uplift. And so just be aware, that's why we showed not permitted here. So we could go with a segmented wall for 1-1 and get rid of all the straps. That means we've got hold downs around all the segments. So those are some of your trade-offs that you look at when you're doing the design, but that's how it shows up in some of these tables. Also, just want to point out this note down here at the bottom of page 67 that about with the anchor bolts and the 3-inch by 3-inch steel plate washers. Let me just show you a drawing on that, because if you're going to use the wood structural panels to resist uplift, this is from the special design provisions for wind and seismic, and let me blow this drawing up here just a little bit so you can see it a little bit better. It's going to require that you use 3 by 3-inch steel plate washers on anchor bolts at 16 inches on center, and that's because you got to make sure you don't exceed the cross grain bending capacity of those bottom plates or sill plates. And so that 3-inch by 3-inch washer is within 1/2 an inch of the wood structural panels, because now you're taking uplift through those wood structural panels. And so the detailing has got to be such that you're always within 1/2 an inch of your sheathing on the outside. For a 2x4 wall, it's real easy. For a 2x6 wall like here, you're going to have to offset or use slotted plates to make sure you can get out to within ½ inch of that wood structural panel. So make a note of that, and just be aware that that's another detail that you have to account for if you want to use wood structural panels to resist uplift. The other thing for you engineers in the audience is the new wind and seismic standard, the 2015 version, allows you to go greater than 16 inches on center, and so that's something else that that you can be aware of. All right, so next to page 68, and I'll ask Brian to come back and do another poll question for us.
Okay. Whoops. There we go. Here's our next poll question. When wood structural panels are used to resist wind uplift and shear anchor bolt requirements include which of the following? A, 3x3 steel plate washers. B, spacing at 16-inch on center or less. C, A and B. Or D, none of the above. And I'm going to close the poll now. And let's take a look at the results. 20% of you said A, 4% of you said B, 70% of you said both A and B, and 7% said none of the above. So, buddy, what's the correct answer?
All right, so the correct answer is C, and I'll point that out to you one more time here, bottom of page 67. If we're going to use the wood structural panels to resist both uplift and shear, we're going to require those 3-inch by 3-inch steel plate washers and at 16 inches on center or less, and detailed like we showed over here in the wind and seismic standard. So answer C is the correct answer there. All right, so let's talk about hold down design, and again, to just talk about something new, and this is for overturning resistance, not uplift. So for you folks out there on the West Coast, this is for wind or for overturning resistance, as opposed to uplift that we talk about for wind design. So we're sizing our hold downs for those various walls, and to do that we look at table 317F, and I'll just go ahead and turn there since it's such a simple table to navigate, and it'll allow me to just talk briefly about one of the things that is often asked about this table and why the values are so simplistic. It's because we're assuming, for example, we've got 9-foot walls in this particular example, so the wind hold down capacity is 3924, the seismic hold down capacity is 2151. It's the same whether we're talking about the segmented or the perforated shear wall method, and the reason for that is that we assume that end panel in the wall where the hold down is located, whether it's the segmented wall or the perforated wall, is going to pick up 100% of its capacity before it sheds load into the rest of the wall. That is a conservative assumption. You as an engineer have the ability to design hold downs differently per the wind and seismic standard. And so just know that the wood frame construction manual, as a largely prescriptive document, does have that conservative assumption built in. It allows us to greatly simplify the assumptions in these tables. The other thing I'll point out is the footnote here that says the required hold down capacities assume wall sheath per our standard detail, which is 6 and 12 inches on center. For other wall sheathing types and tabulated capacities, you're going to divide by the appropriate sheathing type adjustment factor from table 317D. So back to our workbook for seismic, we were at 3 inches on center, and that sheathing adjustment factor was 0.53. And so because the shear wall, or because the hold downs are based on shear wall capacity, we can now bump up that hold down from the 2150 to 43 or 4,000 and let's see, to 4,058. And then we got to remember that that's additive for the hold down from the top floor. So any hold downs that are coming through from above, from the second floor, are additive with that, and that's why we show a cumulative hold down capacity at the foundation of 6,200 pounds. We're going to do the same exercise for wind. Those were at 4 inches on center. There's an adjustment factor there of 0.74. So the adjusted capacity is 5,300 pounds. We're going to add to that the adjusted capacity or the capacity from the second floor, and we end up with about 10,000 pound hold downs around the perimeter of the building, and that's for the that's for the perforated shear wall method. Okay, so that 4 inches on center for the perforated method, it gives us a cumulative capacity of about 9,200, 9,300 pounds. Take a look at the note here at the bottom. One hold down can be used on each corner if we've got the corner studs detailed appropriately. So jump back over here to the wood frame construction manual, table 317F. Take a look at the nailing requirements here for nailing those walls, 216 penny commons, to make sure we've got shear transfer between the walls. Allows us to get by with one hold down in the corner rather than putting a hold down on each wall. So with a combination of the perforated shear wall method, which allows us to get the hold downs to the corner, and detailing properly here, in this case we're showing a 4-stud corner and enough nailing to get the shear between those two walls, we can get by with one hold down in the corner of this building. So that's our hold down design. Again, we work hard to get the perforated shear wall method to work to get those hold downs to the corner, and then we've got some other things that allow us to really simplify the process. Now you've got 10,000 pound hold downs. Those are pretty good size hold downs, but those are all in the corners. You've got to make sure you've got load path all the way into the foundation, so you've got to make sure you've got enough concrete in the foundation as well to carry that 10,000 pound load. But we'll look at the details in a second and see what the alternative would have been with the segmented method. All right, so we talked about sheathing and cladding attachment. We won't spend any time on that, so we're going to skip past page 69. We talked last week about the header connections around our headers that handle both the lateral and uplift loads on the headers for wind design. We'll look at our wall detailing summary at the top of page 71 for seismic design. You see our walls were 2x6 number 3 in stud. They're 9-foot walls, but we were able to get by with 6-inch perimeter edge nailing for the segmented method. The SW is a segmented shear wall. For the perforated shear wall here, we were at 3 inches on center around there, but we're going to fully sheathe that wall, and the hold down capacity is going to bump up for that. And when we bump up that hold down capacity, remember we got to increase the shear nailing at the bottom of that wall. So those are just some of the nuances for the seismic wall. For the wind wall, we were still able to get number 3 in stud to work. Gypsum's going to be blocked in some cases, so we'll talk about that in a second. For the segmented wall, we got 4 inches on center to work. For the perforated wall, it ended up being 3 inches on center. Our hold downs at the corners were close to 10,000 pounds. And remember then we've got, because we're using the wood structural panels to resist both uplift and shear, we've got those 3 by 3 inch anchor bolts at 16 inches on center. And also, again, we've got the shear nailing along the bottom of the shear walls to the floor diaphragm. So there's a construction detail summary. The graphics then give us a real good sense of what's going on in those walls. And we're going to look at this one here at the top of page 72. This is our perforated shear wall. Again, almost 10,000 pound hold downs. The nailing is 3 and 12 around the perimeter. And it required blocking for gypsum if the aspect ratio exceeds 1.5 to 1. So just remember that blocking might be required. In some parts of the country, they're laying up their panels horizontally, their wood structural panels horizontally, so could potentially kill 2 birds with 1 stone there with blocking for both your wood structural panels and your gypsum. But let's compare that to that segmented shear wall. So in that case, it required almost 22 feet of full height sheathing. So we can actually skip between the 2 windows here. We don't necessarily need the full height sheathing. But look at all these hold downs that are required. And these 8,000, 7,900 pound hold downs here are picking up load from above, from the 2nd story. So we're accumulating that down through the structure. These 3,900 pound hold downs here in the middle are for a window from above that would have to be transferred down into the foundation as well. So you see, again, the pretty distinct difference between the perforated method and the segmented method. So let's see, anything else we want to point out there before we bring Brian back to do that last poll question? Yeah, let me just mention one thing. That's this note down here at the bottom. So down here in red, or at the bottom of your printed copy, we know that you're probably not going to use different types or different capacities of hold downs around the perimeter of the building. We're showing here the exact hold down capacities that would be required. You'd probably pick the largest one. In this case, it's a 10,464 pound hold down that's required for this wall 1-2 or 1-1, sorry, for the south elevation. Use that at all 4 corners. Even if you were doing the segmented method, you'd probably pick up the largest hold downs and use those consistently around the slab. So we're showing them there just to give you a sense of the differences that you're going to pick up in the design process. We know from a practical standpoint you're going to use probably the worst case nailing requirements, worst case hold down requirements around the perimeter of the building. But we hope you get a sense that we've designed a building now to resist 160 mile per hour exposure B wind loads and seismic category D1. So that's, if we can get it to work here, then you can get it to work in a lot of places that you're going to be located around the country with lower seismic and wind loads. So Brian, let's take a look at that last poll.
I also just wanted to point out the time. Do we have enough time for another poll?
Yeah.
Okay.
Yeah, let's do this last poll, and then we'll have you close us out, and then we'll come back for Q&A after you close us out. So let's take a look at this poll.
All right, here's the final poll question. Bringing it up now. Which of the following is false regarding gypsum used in shear walls? A, it can be used in a shear wall to resist wind loads. B, blocking is required when aspect ratios exceed 1.5 to 1. C, it can be used in a shear wall to resist seismic loads. And D, the max aspect ratio is 2 to 1. So I'm actually going to just allow 2 more seconds and close this out. Okay, here we go. And here's the results. 8% say A, 9% say B, 71% say C, and 13% say D. Buddy?
Okay, so the correct answer is C. Gypsum cannot be used to resist seismic loads. And I'm going to take you back to table 317D and some of the footnotes here and the capacities shown in the table for, and we mentioned this earlier, that seismic loads are lower because we're not counting gypsum there. The footnotes down here at the bottom of that table 317D talk about the maximum aspect ratios for gypsum, and so just be aware of those differences. So I'm going to turn this back over to Brian and have him wrap us up here, and then we're going to come back for some Q&A. Pete's going to be sending me some questions, so get those in the question box as we wrap up. Brian?
Okay, great job, buddy. Okay, everyone, here's some more quick info. Our partner organization, Woodworks, provides wood project assistance and other resources. If you want to reach out to them, email help@woodworks.org or visit their website. In order to help design professionals stay informed about technical issues affecting the wood industry, AWC offers design professional membership. There are lots of benefits, including discounts on our publications. Check out awc.org/membership if you're interested. AWC also offers a special program for qualifying code officials. As you can see on this slide, there are a lot of benefits associated with this program as well. If you're a qualified code official, we encourage you to sign up at awc.org/codeconnections. And as I said earlier, give us about half an hour to run reports and keep an eye out for an email from AWC. Complete the survey for a chance to win a free publication. Look for information about your certificate of completion and continuing education credits. The actual certificates will be available within 2 weeks of today. Please give us those 2 weeks as we have a lot to process. Remember that in order to receive credit, you must have been present for 90% of this 1-hour webinar. That's 54 minutes. Coming up on June 23rd, we'll have a webinar on fire resistance design for wood construction. Also available is our self-directed study program, which you can find in the education section of awc.org. If you want to book a live presentation, just contact us. And if you have any other questions or if you're looking for more information, email education@awc.org or visit our website. And that wraps up everything for me. I'm going to toss the ball back for some Q&A time.
All right. Thank you, Brian. And I'm going to pull this back to my screen just so I can use some of the documents here to answer some of these questions. The first one says, can I use floor joists, or can I design floor systems using i-joists? So I want to direct you to Chapter 2 of the Wood Frame Construction Manual. It's a really good question, page 20, Section 2.3.2, Wood I-joist Systems. And note that the text here, the very first section, says that single and continuous span I-joists shall be in accordance with the capacity requirements in Table 2.8 A and B. So I'm going to jump to Table 2.8 A and B, and 2.8 is a floor framing capacity requirement for a 30 pound per square foot live load. And you see within this table we show capacity requirements, apparent rigidity, moment, bearing, moment and bearing for different live and different dead loads and deflection requirements. So using these basically MV and EI tables, you could design engineered products into the floor system. That's the beauty of Chapter 2, is it pretty much spells out all the loads, both gravity and lateral loads, that we use in Chapter 3 to then provide a solution for commodity products like lumber and connections. But it still allows you to use proprietary products such as i-joist and the proprietary connectors with the load tables that we develop. Next question, what diaphragm loads are used in calculation of the top plate splice requirement in 321C? I think this was asked last week. To help answer this question, I've got the commentary here. See, actually, let me answer another question that came in while I'm here on this page. Table 3.2C. This is the sill or bottom plate to foundation connection requirement for resisting uplift loads. Somebody wanted to know, okay, well, how do you size those anchor bolts for uplift loads? And what we're doing there is we're looking at both the bending capacity and the compression perp capacity of the bottom plate or sill plate. So for the uplift loads, we come in here and we're going to calculate number 2 Southern Pine sill or bottom plate exposed to weak axis bending, and then we're going to also check compression perpendicular to grain. So if you don't have the commentary in front of you, this is one of the documents that's available when you purchase the set, the wood frame construction manual, either in electronic or hard copy format. This gives all the background for all the various tables and calculations that are used. Now the next one was about the splices, top plate splice requirements. So I'm going to go to table 321 for those splice requirements. Again, in the commentary, table 321, we're going to use the ASD unblocked diaphragm capacity and assume that that diaphragm is going to reach 100% of its capacity in order for us to simplify the calculation of those top plate splices. If you have actual loads on the building and you want to engineer that for the actual loads, you're certainly free to do that with the wind and seismic standard, but those are the assumptions that we make there for the top plate splices. Are there Excel spreadsheets or other calculators available based on the wood frame construction manual? No, we don't have specific spreadsheets available. There is a software package out there called WoodWorks software. We are technical advisors to the folks that develop WoodWorks software. So if you go to our website, look under the software section of the website, you can get a link to WoodWorks, and you can download actually a demo version of their software that does shear wall design, and it does both segmented and perforated shear wall design in accordance with our standards. And so if you're looking for some tools like that, they're out there. We don't make the spreadsheets available that are used to develop the tables in the wood frame construction manual yet. So let's see. Okay, so chapter 23 of the IBC, of the old IBC 2006, mentions that the shear wall capacity can be increased 40%. Is this accounted for in the wood frame construction manual? Yes. So because you saw in the wood frame construction manual in table 317D, we'll jump back there again, that's one of the most helpful tables in the wood frame construction manual. If you turn to table 317D, you see that we list the capacities there. And those wind load capacities for the shear walls and for the diaphragms are already increased by that 40% adjustment. The current codes already have that built in as well. So that's already built into the shear wall capacity tables. Next question, and probably the last one that we have time for here: where does blocking go within the wall? Does it go at mid-height? Now, blocking can really go wherever your panels break. So if, for example, you're laying up your panels, if you're laying them up vertically and you want to break across and you want to go across the band joist and break at the lower part of the second floor, then you could break at the 2 or 3 foot mark of your second floor. The thing you got to watch out for there is shrinkage of your band joist. So that's something that you need to be careful of if you're using the wood structural panels to resist uplift and shear. you've got some detailing you need to be aware of. The other thing you need to be aware of is cross-grain tension in the band joist and in any blocking that you have in those walls. And so we've spelled out some pretty specific blocking details in the walls if you're going to resist uplift and shear to prevent that cross-grain tension from tearing your blocking apart or from even tearing your band joist apart. So look at the notes and the details in the wood frame construction manual for doing that once you, if you decide to go that path. So, all right, that's about all we've got time for today. We'll be also taking a look at your questions that have come in and answering those after the fact through our help desk. But I want to thank you again for joining us for this 4-part series, and hope you've taken away some valuable information, and come back and see us next month for our fire design webinar in June. Have a great day.